Hello, am I audible? Good evening, everyone. Today is our ninth session on the topic of basic construction materials. So, as in previous week, we have finished about the metals, how different we have different type of metals, and what are the importance of metals in our concrete composites. So, the next thing which we'll talk about, next material which we'll be talking about in this week will be polymers, plastics, and composite materials. So, an overview what you might have studied in this week might be in polymers and plastics. You might have talked about what are the different characteristics of polymers and what are the different effects of drawing, or we can say stretching of a polymer. What is glass transition temperature, different type of polymers. Mainly, we will talk about thermoplastic and thermosetting, and then we have third type elastomers. So for that, we are talking about viscoelasticity of our polymers. And next thing about the composites. So mainly in our concrete system, we are using fiber reinforced composite. And what are the different nature of fibers and how they are being used in different structure elements. So if we start from the basic thing, what exactly does polymer mean? Poly means many, mers means from a uh, like a small uh, monomer. So if we see means monomer. So if we see from this example, when you are repeating a small monomer at a different time for a different length, that is called as polymer. So in this example, as in polythene, we have a simple monomer of C2H4. So when this small unit will keep repeating itself to make a long chain, it is called as a polymer. Same way in PVC, we have one H is replaced by chloride, and in case of polypropylene, one H is replaced by CH3. So this is a few example of polymers, simple polymers. Then if we talk about what are the different characteristics of polymer, or what are the different configurations of polymer. So if our different polymers are just going around, are chained around, and they have very weak bond among different chains, that is called as linear polymer. However, if our linear polymer have some branches, that is called as branch polymers, and the interconnection between these two branched polymers will be a weak van der Waals forces. So and the next type is cross linking. So in cross linking, what is happening, different chains of polymers, they are interlinked to each other with a strong bond, mainly covalent bond, that is called as cross-linked polymer. And lastly, it is the network. So network is like we have benzene and all different polymers are connected in a network kind of condition. So more the complexity, more will be the strength of your polymer. So this is if we talk about if we talk about strength value, more the complex combination, or more the stronger bond we are using to combine, more will be the strength of your polymer. And other things are different characteristics of our polymer. So first and foremost important characteristic is the molecular weight. So more polymers are there, bigger chain will have more molecular weight. So it is directly proportional to the chain length. So more the larger the chain, more will be the molecular weight of your polymer. Second thing about second characteristic of polymer is about the crystallinity percentage. So if we see a cross sectional of a single polymer, it will have some crystal structure and some amorphous structure. These things we have talked about in initial lecture, how this cross section is being developed. So, this is missing. This is a crystal region, and that is an amorphous region. So based on this thing, we can calculate the percentage of crystallinity. So what will happen? More the crystalline structure, more will be the tensile strength, or more will be the modulus of elasticity of your material. And how this crystallinity, we can increase this percentage? We can increase this percentage by annealing our material. So you remember annealing, right? Annealing is when we are increasing the temperature. So that in that way, we can increase the percentage of crystallinity in our annealing, means increasing the temperature and slowly cooling it down. So in that way, we can increase the crystallinity of your material. So other important characteristics of polymer, if we talk about, we are dividing our characteristics in two parts: structure and behavior. So in structure, if we talk about molecular, then as we have seen our molecular structure, it can be linear, branch, cross-link, and molecular size and mass, which will be directly proportional to the length of our chain. Other type of structure characteristics are molecular organization, if we are talking in the bulk or if we are talking on the surface of our polymer. So depending on our what we say, um, what type of bonding is there on the structure, if we have gaps, and what is the structure of bulk, like in this example, if it is crystalline or amorphous, depending on that, our properties of polymer will change. Other things is behavioral characteristics. Mainly we will talk about, if we talk about behavior, it is mainly the mechanical characteristics, or like tensile response. So if we go to the tensile response of our any polymer, what we can see, uh, this is how a normal polymer tensile strength will look like. So what is happening? These are two type of behavior we are talking about: brittle failure and plastic failure. So in brittle failure, what is happening when we are stretching our polymer, normal polymer, it is uh, it is aligning itself and then it is breaking from that point. So if our material is brittle, in that case, we will have this kind of failure. And in case of our plastic failure, we are it's a semi in different type of in different type of material. If we have amorphous material, crystalline material, semi-crystalline material, the behavior of our polymer will be completely different. So if we talk about a crystalline material, if we have more crystalline region, there are chances of formation of necking. A necking will be formed and it will stretch more, and it will have a higher tensile strength. It will have a higher strength as compared to the, talk about amorphous or semi-crystalline. In case of semi-crystalline, what is happening? It is breaking. It have a very low necking, very low necking region, or we can say very low yield strength as compared to the crystalline material. Next thing is the when this material is stretched, necking will be forming, and at one point these fibers will break, or this polymer will break at some point, and then we have a plastic failure. Also, this region where necking is happening, this is called as our elastic region. So because of mainly when we have a low temperature, at that point we will have, in case of low temperature, we will have a brittle type of failure. In case of higher temperature, we will have a plastic type of failure. So next thing is effect of drawing. So what is drawing means? Any polymer, when we are stretching it, it is called as drawing. So if you take an example of your rubber band, when you are stretching it, there are chances it at till one point it can come back to its original place. But once if you see some fibers are getting break like this, and at that point there is no chance of coming back to the elastic state. It will break itself. So that is how drawing will affect your uh, properties of your polymers. So if we are annealing after drawing, what will happen? It will decreases your alignment and it will reverse the effect of drawing. So if you are heating your polymer after drawing it, there are chances that it will reverse the effect of your drawing, if reverse the effect of this stretching and change in the molecular structure of your polymer. And so this is how a normal polymer behave, a brittle or plastic failure. Next thing is elastomeric case. Elastomeric means within your elastic limit. When you are talking about elastomers, the uh, the stress strain curve of a normal elastomer is completely different as compared to your brittle or plastic failure. It will have a very low strength value. However, it will have a long elastic region in it. So till one point, your deformation is reversible. That is called as elastic region. After that, there is no reversible, deformation is not reversible. However, it is not a breakage point. Breakage point is when your fibers start breaking it from any point. At that point, you will have a failure. So that is in the case of elastomeric materials. Other type of properties, if we talk about in our polymers, is mainly depending on the thermal properties. So what is happening when with the change in temperature, we have two type of temperature. We have glass transition temperature and then we have melting temperature. So what does glass transition temperature means? Glass transition temperature is the temperature at which your material will change from a solid to viscoelastic material. A completely elastic solid will changes to viscoelastic solid. And if you see from this graph, in case of amorphous material, uh, you have a very defined glass transition temperature. However, when we talk about crystalline material, in crystalline material, there is not a proper glass transition temperature. Material is directly change, converting into liquid. It doesn't have a viscoelastic behavior. A solid will directly change into the liquid in terms of crystalline material. However, in amorphous material, you will have this glass transition temperature where your solid or your elastic material will first change into viscoelastic material and then will convert it into the liquid formation. And this thing can be seen from this graph also, how different type of materials will have different type of properties depending on the molecular weight. So with the increase in temperature, if we talk about at any point, if we talk about at this point, at with increase in temperature, what is happening? Your crystalline solid is directly converted into mobile liquid, right? However, if we are increasing the molecular weight of our crystalline solid itself, there are chances that it will have a viscoelastic behavior. So both factors will affect your volume and your temperature. So if at a higher molecular, your temperature and your molecular weight. So a same crystalline solid at a smaller molecular weight will directly convert into the liquid. However, if you increasing the molecular weight or if you increase the chain length, what is happening? There are chances that it will have a glass transition temperature. It will change into viscous liquid before converting into the proper liquid. And if we talk about the partially crystalline solid, it will convert it to tough plastic and then rubber material, and then it will break. Okay. So this is how molecular weight and temperature will affect your properties of your polymers. So next thing, if we from this week, if we talk about two type of polymers, mainly thermoplastic and thermosetting polymers. So thermoplastic polymers are like the polymers which we have different chains, and these chains are interlinked to each other with weak intermolecular forces, mainly van der Waals forces. In thermosetting polymers, what is happening? Different chains are interlinked to each other using cross-link bond or with a strong covalent bond. In this case, they have weak intermolecular forces. In this case, it have a strong covalent bond. So if we see an example of thermoplastic, if we have polythene or rubber band, so there are chances that when we are stretching it, it will come back to its original position till some point. And if we see the example of thermos setting, if in thermosetting, what is happening? It, for example, epoxies, it will break, and even if you are increasing the temperature or something, it will just break. It won't come back to its original position. And other properties, when we are heating it, this type of material will soften. However, this type of material will remain hardened and will directly break. So this is the main difference between thermoplastic and thermosetting materials. And other thing is this thermoplastic behavior of different materials. So how temperature will affect the properties of thermoplastic materials. So if we talk about at higher temperature, this material will soften and will have a more elasticity. However, at lower temperature, if you take a rubber band and take it to a very low temperature, or if you keep your rubber band in a freezer and in a normal temperature. So in normal temperature, you will be able to stretch it till a longer time. However, if you keep it in a freezer and your rubber band is in a very low temperature, let's say -2 degrees Celsius, and when you will stretch it will just break down. It will have a brittle behavior. So that example you can understand from this graph. At higher temperature, it have a more elasticity, and at lower temperature, it have a higher brittle nature. So that is about the thermoplastic behavior of your materials. Next thing is about the viscoelasticity. So what is viscoelasticity? Viscoelasticity is a transition region from liquid to solid. So materials uh, which have properties in between solid and liquid are called as viscoelastic material. And what is happening in case of viscoelastic material is there is with time the stress value or the strain value will decreases in case of viscoelastic material. And in other thing is in the creep, if we talk about the creep value of viscoelastic material, it will have a higher creep value as compared to your normal uh, as, as compared to your normal material or metals or something. That will have viscoelastic polymers will have a higher creep value. So this is all about the polymers which you have studied in your lecture. Examples of polymers where these type of polymers are used in your structures. If you might have studied in, you might have listened to the lectures in, mainly if you remember, we are using for earthquake resistance. We are using these type of bedding, and they are made of which are called as bearing pad. We are using this bearing pad. They are mostly made of polymers. So they have high, what type of strength? Any idea? Have high reversible strains, and they can high elasticity or uh, high elasticity and high tensile strength. Not tensile strength, sorry, high elasticity. Because of that, it can come back to its original position and can transfer load from superstructure to substructure without failing. So this is all about polymers. Is Next thing is about composites. So what is the definition of composite? It is a combination of two things, that is a matrix and dispersed material. So if we are adding something in a larger matrix, it is called as composite. So for example, if we are adding fibers to our concrete, that is a fiber reinforced concrete composite. So in that case, our matrix will be concrete and our fibers are the dispersed phase. So these are the different type of classification of composite materials. We have particle reinforced, then we have fiber reinforced, then we have structure composite. If we talk about particle reinforced, means we are dispersing some particles into our matrix, like we are using some small steel fibers and we are dispersing them into concrete, that is particle reinforced. Then is fiber reinforced. Fiber reinforced means like in textile reinforced concrete, we are using a sheet of complete polymers, sheet of fibers in the concrete matrix. The last thing is structural. In structural level, what we are doing, we are using complete laminates of polymers in between our concrete. So if we talk about this bearing pad, it is kind of structural composite. This is not a composite. This is just a polymer. But example is like you have a structure elements in between. You are using your polymer. That is a type of structural composite, or we can say sandwich panels. We have one layer of material, another layer of same material, and in between we are using dispersed phase. That is a structural composite. So how we are mixing, rule of mixture, we have talked about phase diagrams in initial lectures. So that same phase diagram we are using in this case. When we have to calculate the upper limit, these are the two composites. We are adding copper in tungsten, copper in tungsten we are adding. So a different percentage of copper, uh, what we are doing, we have a phase diagram where this is a liquid phase, this is a solid phase, and this is liquidus line, solidus line, all these things we have talked about in initial lectures, right? So if we have to calculate this upper limit, the formula we are using is EC. EC is our modulus, is equal to VMEM plus VP And in case of lower limit, we are using the parallel function. 1 upon EC is equal to VM upon EM plus VP upon EP. So if we have to understand this thing clearly, what is happening is at upper limit, our materials are uh, in parallel case, they are in parallel form and we are applying load on both ends. So what is happening? Complete load is distributed to both panels. So P is equal to P1 plus P2 and our modulus will be same. E is equal to strain will be same, strain will be same in both panels. So strain is equal to E1 is equal to E2. So if we talk about strain is equal to sigma is equal to P upon A, right? So from P is equal to P1 plus P2, we can calculate P is equal to sigma into A. So sigma into A of the composite is equal to sigma 1 plus sigma 1 A1 plus sigma 2 A2. So, solving these two equations, next thing is we know that E modulus is equal to sigma upon strain, stress upon strain. So same way we will convert stress to strain. So strain E1 is plus E2 A2 and divide same way this side we are doing. So eta is equal to eta 1 eta 2. So that can be cancelled from all these cases and this will give us complete value of modulus is equal to E1 A1 upon A plus E2 A2 upon A, which can be called as E1 V1 plus E2 V2. So V1 and V2 are the volume fractions. Same way, if we talk about the lower bound, in lower bound what is happening, both the materials are in a series kind of structure and load is applied in this case in this way. So what is happening when we are applying load? Both the panels are facing equal load. So P is equal to P1 is equal to P2. However, in this case, what is happening? Strain is divided into two parts. So E is equal, eta is equal to eta 1 plus eta 2. Same way, in this case, we are taking from the deformation point of view instead of taking from the stress value, we are taking deformation. So deformation is equal to strain into length, right? Then again, we are taking strain is equal to sorry, L1 we will divide it by completely by L. So strain is equal to E1 L1 upon L, E2 L2 upon L. Again, we will convert strain into from this formula sigma upon E is equal to sigma this same thing. So if our load is same, our stress value will be same in both the materials. So that's why we are cutting sigma 1 and sigma 2, and this will bring us to the equation this 1 upon E is equal to V1 upon E1 plus V2 upon E2. So that's how you get this upper and lower limit. Okay. So this is how we are calculating our upper and lower bounds. Other thing is, what are the different example of composite? So if you can see in this case, in our normal steel material, in our steel we are telling it is a TMT rebar, right? So it have a carbon is dispersed into the iron. So it have Fe3C phase, it have a normal ferritic state, normal iron, and carbon based iron particles are divided into it. That is a normal spheroid steel. Other example is when we are using for example, in this case, we are using different cobalt matrix is there, and we are adding some brittle or hard materials as a particles to it. That is a cemented carbide type of. Same way we can have different type of example of composite. These are the particle based examples. If you see from here, we have divided in three parts. So if we talk about particle reinforced, so these are the example of particle reinforced. We have different particles in our matrix. Next thing is fiber reinforced composites. So in fiber reinforced composite, we are adding different fibers to our matrix, and how the different alignment of our fibers will affect the properties of our concrete composite. If they are aligned in same way, if they are aligned in a random way, how they will affect the properties of your concrete. And for better fiber efficiency, what should be the fiber length, how we can calculate the fiber length in tensile strength. It will depend on your fiber diameter and what is the shear strength required for the fiber matrix interface. So all these things you have already studied in your lecture, so I won't go in deep. And next thing is how fibers nature will affect your properties. So this is a stress strain curve, and this is normal stress strain curve of RC steel, and this is stress strain curve of pre-stressing steel. So mainly what we are telling, we are replacing a normal rebar from the fiber reinforced rebars. So FRP bars are there. So we are using three type of FRP bars: carbon, aramid, and glass type. So this is a stress strain curve of different type of FRP bars. So if from this you can see that it have a carbon will have a higher yield strength as compared to aramid and glass. However, none of them have a high ductility. They all are brittle in nature when we compare them to the our normal steel or pre-stressing steel. You can't see any uh, ductility part or any strain hardening in case of your FRP rebars. So mainly our fibers are brittle in nature. However, they have a higher tensile strength as compared to our normal steel bars. So where are all these type of fibers being so this is about the FRP rebars. Other than this, where all we are using FRP bars are, we are using them as for the pre-stressing of bridges. So these are pre-stressed. How they are pre-stressed? So laminates are being pasted. So from one end, they will anchor it, and then they will stretch and anchor from the other end. So in this way, your FRP bars will be behaving, your FRP laminates will behave as a pre-stressing laminate, a pre-stressing uh, laminates. Next thing is we are using it for the retrofitting. So if you have seen on columns and beams, mainly we are pasting the FRP's laminates over the concrete, and they will have they will prevent the crack enhancement. So that is a type of retrofitting. Other than this, we can use it st- uh, as a fibers in structure composite. So this is a textile fiber reinforced composite. So we are using FRP laminates as a partial as a replacement to normal rebars. So these are the normal laminates, normal FRP or textile reinforced polymer, which are been added to the matrix of concrete to give it a good tensile property. So that's all you might have studied in week 9. If you have any question, you can ask. Otherwise, we will go to some question answer for this session. If there are no doubts, then we will see some question answer. So PH2 is the building unit of polypropylene, polystyrene, polythene, polyvinyl chloride. So that we have seen in first lecture itself. Any guess? So it is a basic unit of normal polythene. So in case of polythene, we have a monomer of CH2, 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 which is being repeated in multiple times, and this is a monomer for polythene. Okay. Okay, so the next question is, stretching of the polymer prior to its use is called as annealing, tempering, quenching, or drawing. D, correct answer. So we have seen when we are stretching our polymer before using, we call that properties as drawing of our polymer. Next question is, choose the correct statements. Drawing increases modulus of elasticity, it decreases the ductility, it increases the brittleness, or it increases the tensile strength. So more than one statement are correct. Any idea? So when we are when we are drawing our polymer, what we are doing, why we are drawing it, it usually increases the modulus of elasticity. So if you have seen that graph of polymers, so if we are drawing it, this modulus of elasticity is increasing. And then next thing is, how if you are increasing your modulus of elasticity by default, your ductility will decrease, right? this area will decrease. Your strain hardening would decrease. And next thing is it increases the brittleness. No, it won't change the brittleness, and however it will increase. Yeah, A and D are correct answer. However, B is also correct. So increasing modulus of elasticity will definitely will decrease the ductility of your material. Okay, so the answer correct is A, B and D. Next question is, which property distinguishing thermosetting polymers from thermoplastic? So thermosetting polymers soften on heating, can be reshaped multiple times, can undergo permanent chemical change on heating, they have low melting point. B, okay, correct. So when we have seen about thermoplastic and thermosetting materials, we are telling when we are heating our thermosetting materials, it will remain hard and will change the have a permanent change to the material. It won't come back to the original shape. Correct. C option. What is the key difference between polymer concrete and polymer modified concrete? So the polymer concrete uses polymer as a full binder, whereas polymer modified concrete contains polymer additives in cement. Polymer modified concrete has no cement. Polymer concrete is more permeable than polymer modified concrete. Polymer modified concrete cannot be reinforced. So we didn't talk about these type of concretes. So if we talk about polymer concrete, what are the polymer concrete means? We are replacing our binder from replacing our binder fully to polymers. So where these type of materials are used is like when we have expansion joint. At that point, when we are adding this polymer, that is normally called as polymer concrete, because what we are doing, we are uh, replacing our concrete with polymer. And in case of polymer modified concrete, we are adding our polymers into the matrix of our concrete by replacing cement or by just adding as an additive. So now from if we see from this examples from these options, it uses polymers as full binder, where polymer contains polymer additives in cement. So this is the correct option. Contains no cement, no. Polymer can be more permeable. The polymer modified concrete, no. Concrete cannot be reinforced. Wrong. So the answer will be A. Okay. So the next question is, molecular weight of the polymer is the mass of mole of chain. Correct? True or false? Yes. A. Correct. So we talked about molecular weight of a polymer. So as we increase the chain, our mass will in increase. So it is the mass of the moles of chain. True. So seventh question is, which of the following is an example of thermosetting polymer? Polystyrene, polyvinyl chloride, bakelite, polythene. So thermosetting polymers are the polymers which have cross-linking, and which cannot be come back to the elastic state after heating. So which of these do you think is the example of thermosetting polymer? So answer is bakelite. So all these things, PVC, polystyrene, polythene, they can, from the name only, you might know that these are the thermoplastic materials which can be converted back to the normal elastic state after heating up. However, bakelite, what is exactly is a bakelite is? Any idea? So mainly when we are, if you have seen switchboards in all these type of plastics in your normal home switchboards or sockets, or you have toys made of it, that plastic is made of bakelite. Okay, so that is a thermosetting polymer. Next question is, crystalline materials exhibit melting temperature as well as glass transition temperature. True or false? True. Okay. Answer is actually false. If you, I don't, I have that graph. So if you see from just a minute. So in case of crystalline material, there is no glass transition temperature. There is a direct conversion of crystalline material to liquid form at with increasing temperature. So C is your crystalline material graph. So in crystalline material, there is no glass transition temperature. Therefore, in crystalline material, glass transition temperature is not there. That's why the answer is false. Okay. So what happens at the glass transition temperature of a polymer? Why we are calling it as a glass transition temperature? The polymer melts into the liquid. The polymer becomes brittle and glassy. The polymer undergoes chemical reaction, or the polymer evaporates. Actually, none of the option is correct. It doesn't melt into the liquids. As we have seen, it will go like this. This is your liquid phase and this is your transition phase. So what is happening at glass transition temperature? It is becoming from solid to viscoelastic material. So it is actually converting from hard and glassy state to soft state, soft or rubber kind of state. So at glass transition temperature, it will convert from polymer becomes soft and rubbery from brittle and glassy. So that will be the correct answer. Okay, I will modify this question and then upload the video. Okay, so the next question is, So we talked about it is changing from solid to viscoelastic. But what exactly is the primary molecular changes that is happening at the glass transition temperature? The chains become mobile and flexible. The polymer chain crystallizes completely. Polymer decomposes. A polymer changes from solid to liquid. So at molecular level, what is happening that your polymer is converting from solid to viscoelastic material. Your what is happening? Your chains are becoming more mobile and flexible. Because of that, your material will become much more softer. Okay. Any doubt? The next question is choose the correct statement or statements. As the molecular mass weight increases, tensile uh, as molecular mass weight increases, tensile strength increases. As the length of chain increases, molecular weight increases. Annealing reduces crystallinity. As crystallinity increases, tensile strength decreases. As crystallinity increases, modulus of elasticity increases. So one thing we all know is length of chain increases, molecular weight increases, right? Any other option you think is correct? A and B, okay. As molecular mass increases, tensile strength increases. Any correct. So as the mass weight increases, your strength will also increase. Any other option from C, D, and E which you think is correct? So we talk about increase in crystallinity. So if your crystal structure increases in your material, your modulus of elasticity will increase. So this option is also correct. And tensile strength will also increase, it won't decrease. So answer is A, B, and E. Okay. Okay, so the next question is what type of polymer behavior is shown in the viscous liquid region area? It is elastic deformation. It is flowing behavior due to chain mobility. It is rigid structure with no movement, or it is a brittle fracture. What is mobile in previous question? This one. Mobile means in what we say moving condition. Means instead of being at a fixed position, your polymer chain will start moving and they will become more flexible. Mobile means moving. Okay. So what is happening in the viscous liquid region? So in when we talk about glass transition temperature also in viscous area or in during glass transition temperature, your uh, chain will be in mobile, will have a mobility. It will be in moving condition, and because of that, you will your material or your solid will have a flowing behavior or viscous behavior. Okay. The next question is, as the bar diameter increases, the strength of glass fiber reinforced polymer will increase or decrease. So this is your glass fiber reinforced polymer. reinforcement. If we are increasing the bar diameter, what is happening? The strength will increases or decreases? So if we increases your bar diameter, what is happening? No, the strength will decrease. How it is decreasing is if you increases the bar diameter, the fibers or the normal polymer chains, they will have there are chances of more weak points in your chain. So normally we are using this bars in tensile area. So if you have more defects in your material with increase in diameter, what will happen? This defects will be more prominent and your strength will decrease. And other thing is, uh, if you have a higher diameter, the bonds between this, already we know that bond between our fiber reinforced and our concrete will be low. If you increases the diameter, that bond strength between your fiber says reinforcement and your concrete matrix will be more weaker, and it will decreases the strength of your complete matrix. Okay. Plasticizer are added to the polymers to improve its strength, resist aging, improve ductility and toughness, or reduce the stiffness. So in polymers, we are adding few plasticizer. Okay, it will improve its strength. So normally, when you are adding any plasticizer to polymer, it won't affect the strength of your polymers. How? Because we are telling our strength value of your polymers will highly be affected by the what will say fiber length or orientation of your fibers or the type of bonding you have. Okay, and plasticizer won't change the type of bonding. So we talk about cross linking and linear and all those things. So adding plasticizer to polymer won't change the type of bonding to your of your polymer. So it won't improve the strength of your polymers. So what exactly polymers are doing is they are like in concrete we are adding what exactly plasticizer are doing. Like in case of concrete, we are adding super plasticizer and they are providing steric hindrance between our concrete particles, which improves the workability, right? Same way, the plasticizer in polymer will do the same type of property, will have the same type of effect on sorry, same type of effect on your polymers. They will increase the uh, durability of your property of your polymers. How they are improving the durability is like they will decrease the intermolecular forces and will increase the ductility of your material. Or so what is happening? So it improves the ductility of your material. So and make the polymer more soft. So plasticizer are making the polymer more softer and are improving the ductility. So if we see from these options, what is happening? It is improving the ductility and toughness, and it will reduce the stiffness of your polymer. mainly where we are using this plasticizer, if we talk about polymer coating. So to have a flowable coating of your polymers, we are adding some liquid plasticizer, which will improve its flow properties. So that is the one example of plasticizer in polymers. Okay, the answer is C and D. It is improving the ductility and reducing the stiffness. In laminates, the orientation of the high strength direction varies with each layer. Some word is missing from here. So in laminates, we are the direction of your layer will the orientation of your layer will matters the most. Why? Because to have ductility in all direction, to have corrosion resistance, to withstand stress in multiple direction. Any idea? So if I talk about an example, if you if we have seen that FRP laminate, right? So what is happening? One layer will be like this, another layer will be like this. So why we are having different layers, then another layer again in this direction, then this direction. Why we are having the different directions and it is varying with each layer is so that it can withstand stresses in all directions. Okay. So why is CFRP, carbon fiber reinforced polymer, is preferred over GFRP for strengthening concrete structure? CFRP have higher tensile strength and stiffness, is cheaper than GFRP, have high ductility, have better bond strength with concrete. So if you remember, we have seen the stress strain curve of different type of FRP. We had three things, and then we have with normal steel, normal steel. So which one had a higher tensile strength out of glass and carbon? This this curve belonged to which one? Remember, it was of carbon. This is glass. Carbon, correct answer. So CFRP is preferred over GFRP because it has higher tensile strength and stiffness. Okay. So the next question is a two-phase sheet surrounding an inner core material of low density will be called as a laminate, a panel, sandwich panel, or plywood. So we are telling a two-phase sheet surrounding an inner core material. This is called as, from the image itself, you can guess what it can be called as. C, correct. So it is a sandwich panel. So the next question is, as the fiber diameter increases, the critical fiber length for longer and thinner fibers will increase, decrease, or does not change. So we will see the formula to calculate the fiber length. Fiber length increases. Okay, so correct answer. So our fiber length is directly proportional to the diameter. So if your diameter is increasing, your fiber length will increase. Last question is the modulus of elasticity of both A and B are 100 GPa. A composite is made up of these two materials in equal proportion by volume of the composite. Answer the following question. Calculate the upper limit for the composite modulus. So you can take 5 minutes to calculate this thing. We have to calculate the upper bound. You remember the formula for upper bound? Okay, I will put the formula here. For upper bound, E composite is equal to volume matrix and E matrix plus, okay, in this case, B, E, B, A. So just take 5. Take A option, 200 GP. Anybody else who have any guess? Okay, so everyone have calculated the answer. So what is given to us is EA is equal to EB is equal to 100, and then volume is divided by two things. So VA is equal to VB is equal to V by 2. So it will be E is equal to uh, E into EA plus EB, right? CB is equal to V. So V is equal to VA VB, which is equal to half of volume. So V by 2 into EA plus EB. Total volume fraction, normally how this formula is coming is we are considering total volume as 100%. That's why this is coming. So will be V total. EL is equal to EL into V total. Option D is the correct. Yeah. So if you use this formula, you will divide it by total volume. So volume will cancel out. Your answer will be EA plus EB by 2, which will be equal to 2 of E by 2 of what will say is equal to 100 GP. The answer is D. Is this clear?
Yes, ma'am.
So that's all for week 9. If you have any doubt, you can ask me now or you can mail me. If there are no doubts, then we will close the class for today. Thank you for joining.